joined Cognitive Design Technology, Silvaco as a TCAD application engineer. In his role, he applied his knowledge to the practical field, contributing to the development and application of technology, computer-aided design tools. A crucial aspect of semiconductor device modeling and simulation. Currently, Franklin is starting new heights in his academic journey as he pursues a PhD at Columbia University. His research focus revolves around gallium nitride high electron mobility transistors, tailored for high frequency RF applications by delivering to the frequencies of this cutting-edge technology. Franklin aims to push the boundaries of electronic communication systems as it creates a use of CAD and EDA and cognitive design technology and explores the creation of gallium nitride in his PhD contributing to the evolution of semiconductor technology and shaping the future of electronic devices. I would like to request Dr. Nitin Sharma to present a sampling to Mr. S.N.G. Thank you, sir. Hello. Yes, sir. Now you can continue.
Thank you for introduction. So myself, Franklin. So I'm PhD engineer in cognitive design technology. So in association with Silvaco. So it's now. And so thank you for your
बटन प्रेस हो रहा है सर
We'll continue with this Silvaco TCAD and its introduction at the beginning, and then we'll go into the mixer circuit simulation tool. So once we see the introduction part at the beginning, and we'll do a circuit simulation. Okay. So the circuit simulation tool which we mainly focus here is the framework we mainly work, which is called mixer mode circuit simulator. So initially we see the circuit simulators. So what are its features and what are its capabilities? What are the things we can do with this? Its syntax, how to write the coding and everything. We look into it, and we directly go into the tool. So initially I'll just show some basic introduction about the tool and what is TCAD, why TCAD, and so on. I'll give you the presentation. And also whatever the code we'll work on, I'll share you that. So initially, the TCAD, if you look into the TCAD, why we made TCAD is so the TCAD, if you see our semiconductor industry, which will rapidly grows, okay, in the past decades, so there is lots of growth. So that is mainly happened due to lots of designers done at different designs. Okay, and they have they reached until the Moore's law, right? So every year that the size of the transistor decreases, right? So they are reducing the transistor size by reducing the channel, by putting different materials, different fabrication process techniques, right? So by these techniques can be easily done through TCAD, okay? So we can virtually do this type of experimentation and everything. So followed by this, what is TCAD? So TCAD is a computer simulation software, okay? So which is basically like you can perform your designs, like not only the unique semiconductor designs you can perform, you can extract its electrical characteristics, optical behavior of your device, okay, thermal characteristics, and not only these characteristics, and also like process design flow, like let's say you deposit some material, okay, so there will be different techniques, there will be some negative effects on the depositing the material, okay, for that you are defining your own idea. So whatever the thing you are developing on your idea, so that you can develop in this tool itself. So why the need is required on TCAD is, so it basically reduces the development cost, right? So because it's basically like we are not physically doing it, we are virtually doing it. Okay, virtually like experimenting the things. Okay, let's say you are choosing some parameters like transfer characteristics. I want this much, frequency this much. So then our device should be at which dimensions and which concentration of dopant profile it should be used. Okay, so everything you are doing in virtually, right? So what will happen is the cost will be reduced, and the second thing is, all other things are like it's very easy to understand, mainly in Silvaco, like let's say if this device is working in such a principle, okay, like you want to visualize its electrical concentration, what is internally it's happening, all those things you can visually understand what will happen, okay. And so you can perform DTCO, which is design technology co-optimization, virtual experimentation, okay, and so you can clearly understand what is happening in your device. Not only the Silvaco supports TCAD on very few sectors, like in a different sectors it will support like displays. So display we can take TFT displays, LCD displays, so currently organic LED displays, QLED displays, okay. So all those technologies we can perform in this device itself. And power, like power that includes like power transistors, you can perform different high power simulations like IGBTs and so on. And reliability analysis also you can perform, like device you can perform breakdown voltage, noise analysis, okay, and different analysis you can do. Okay. The technology sector that comes under optical, which includes laser, solar cell, and all those things. And so the technology that does not exist until now, and you want to create it on your own, okay, you can create your own model and you can develop. That also possible with this chip, Silvaco TCAD. And so let's say TCAD, how it virtually works. Basically, how it basically works, if you have any idea, so I will let you know. So how it works is like, so it uses a physics modeling equations in the background it will do. So let's say like you create one structure, okay, the let's say transistor which contains a channel of silicon and some material for electrodes and doping profiles and so on. So you design it somehow, okay, and how it will extract its electrical characteristics is, so basically it will do kind of sampling of your device, okay, so we call it as meshing, okay. So in this meshing, so drift diffusion equation, electron transport equations, Poisson's equations, so these things will apply on these sampling areas, and it will find out based on your biasing condition, doping profile, material profile, so like a material crystalline structure. So it will extract its electrical characteristics. So basically what will happen is in the background it uses a physical equations. So if you see here, to develop your design is very simple. Like first you have to define the structure, and the second thing is like the what are the models it required for this device. You have to provide it. Okay, and so these models you can easily obtain by initially you can learn it by getting learning through journals, or else like if those models are not available, you can create your own model also. Okay, so that also you can include that. And finally you can apply some biasing conditions and get the data. And the benefit of doing using a physics-based modeling is it's highly predictive. Like if you think of it like so this is my model, and I will apply certain voltage, this should be getting it. So if you have an idea, so you will get almost that. So if your idea is correct, you will get exact. So it's highly predictive. And so the visualization of your device is very clear. Like let's say you apply some, let's say you are doing some reliability analysis like breakdown voltage, okay, analysis, and you are applying high voltage on a gate electrode. Okay, so what will happen is the gate electrode to drain electrode, there will be some defect happens and it will burn out. Okay, so those burn out, how it is happening step by step. Okay, like at let's say the device at breakdown at 50 volt. Okay, so you can choose that 10 volt, 20 volt, 30 volt. So at the certain voltage, you can visually see that how the more number of electron forms and how the burnout happens. So everything is very clearly visualizable by using a physics-based modeling. And so now we will see about this Silvaco products. So that's subdivided by two things, which is a process simulator and device simulator. Okay. So quickly I'll just tell you what is process simulation is. Process simulation is basically you are virtually fabricating your device. So let's say like let's say you have your own fabrication equipments, okay, like E-beam epitaxy and impact ionization, okay, some implantation tools, okay. So these fabrications, you will do certain steps to fabricate your device, right? So those steps, you see, following the same steps, okay, you can create your device. So it will mimic, basically it will mimic your fabrication flow, and it will create the structure. So how predictive and how accurate it will be if you think of it, okay? So let's say you deposit certain material, let's say you are depositing some gallium nitrate material, okay? So based on your temperature, time, okay, and based on some impurity level, okay, so how thickness and how the deposition happens, no? So it will almost 95% it will match that in a simulation, okay? So this is what the process simulation is, and so here we can perform almost all the fabrication steps like diffusion, ion implantation, oxidation, etching, deposition. So all the photolithography process, okay, and so on. So the framework tools we use is, so one is Athena. Athena is a one-dimensional and two-dimensional process simulator. So it will work for only 2D based structures. Okay, let's say you have only a silicon based structure which is on only 2D. Okay. So you can work in Athena, or Victory process is completely like advanced process development tool. Okay. So this framework contains different materials, different advanced materials, ternary, quaternary materials also available. Okay. And also it will support 2D and 3D. So these are the main framework for the process architecture. So the main framework is this S-Supreme core, so which is the core of this process simulator. And you can see here some of the block kits there, like so this optolithography, MC plant. So these things will basically attach and we can work with this. So so I'm not going to depth about this. So I'm just showing you the modules. So these are some simulations have been done with the process simulation. Okay. So you can see here, the first image shows the implantation of the material iron, like N-type, P-type implantation. Okay. And that image shows that they have done a chemical etching. Okay. So you can see the etching has been done through different time period here and the material. Okay. So at the different time period here and the different plasma level, how the etching happens. Okay. It will happen in your physically how it will happen. So it mimics that and it will make that etching process. So these are some examples for the process simulation. So some key features they are given. So the key features are, so as we discussed it, the same thing, like it uses the critical fabrication steps, can be used for CMOS device, bipolar device, silicon based device, silicon carbide device, optoelectronics and so on. So predictive geometry, token, so everything we discussed. So let's move on. Okay. So next is a device simulation. So device simulation is, so you, for example, you have a device, okay, and you want to extract its electrical characteristics or optical characteristics. Okay. So on those cases, we will do this device simulation. So this device simulator is mainly used to extract the electrical, optical and thermal behavior of your device. So here we can perform AC, DC, transient performance and all those things. So the framework which we will be using is Atlas. Atlas is for 2D structures and Atlas 3D is for 3D structures like FinFET, nanowire type of structures and so on. And Victory device is an advanced tool which contains advanced features, so which will support both 2D and 3D. So this is an Atlas device simulator framework. Okay, and the main thing is there is two blocks, which is one is SPICE device 3D and the second one is LACE 2D and 3D. Okay, so SPICE is mainly for silicon based materials like silicon carbide, silicon oxide, right? And LACE is for advanced material like gallium nitride, nitrate based materials, okay, ternary material, compound semiconductor material, so all those things. Okay. So here, so you can see here in the bottom you will see quantum 2D and 3D. Okay. So if people are working in quantum confinement effects like tunneling transistors, the device which has a channel which is less than 5 nanometer devices, so they use this quantum kind of things, right? So on those phases they can use this quantum module, okay, and they can work on. Okay. And So currently we have a transistor which have a channel length which are less than 3 nanometer or 2 nanometer, right? So we have another tool which is called Victory Atomistic, okay, which basically like you are doing a simulation at atomistic level, okay. So the from material wise to structural wise, everything we can work with atomic level, atomistic level. So that also you can check on. And the noise is for noise simulation. Like you can perform all the noise, like noise figure, minimum noise of your device, okay? And like while doing electrical characteristics, you can extract so how much noise it's generating, and all those analysis you can perform. So Luminous is mainly for like light-based simulation devices, like photodiodes. Light-based devices means there is a two types we can split. Okay, one is light-emitting devices, and another is light absorption devices. Okay, so light-emitting means this LED. Okay, yes, laser, V-cell, so those kind of things. And light absorption means it will take the light and it will generate some electricity, or it will convert some pulse like that, like solar cell, okay, photodetectors, phototransistors, and so on. And JICA module, which basically works for thermal-based simulations. Okay, let's say you have a device and you are stressing your device, giving a higher voltage. Okay, and you want to absorb how much heat it's generating. So it's a main thing, right, for a semiconductor, like let's say for a computer processor, if there is no thermal management, the performance drops, right? So we can include this thermal management thermal module, and we can optimize our device. And the final thing is called mixed mode. That's what we are about to look into it. The mixed mode is a circuit simulator, okay, and a device simulator. Okay, so so let's say you have your own device. Let's say a transistor which is you have created using a process or device. Okay, and you want to see that in a circuit environment. Let's say you want to put it in the amplifier. Okay, or like you want to put it in some other circuit. Okay, and you want to analyze its characteristics. Those things we can perform with the mixed mode. And the final thing is C interpreter. C interpreter is like if there is the model or material or the physics which is not exist, and you have your own model, your own material. Okay, so you can include that. You can write that in a scripting, and you can include that, and you can do the simulation. So some simulation done by device simulations, and you can see the graph there. So some are taken from, it was extracted from this. So some key features, okay. So it was accurately, so this device simulator will accurately characterize the physics-based devices for electrical, optical, and thermal performance. Okay. And you can do lots of experimentation with this tool, right? Like you can, let's say, you want to add some material like diamond. You cannot physically afford the diamond substrate in your device, right? So in those cases, you can directly use diamond as a material from the tool, and you can do the experimentation. So basically, it reduces. So without the cost will be cut out several times, right? And also like solve yield and process variation problems also can be identified. Okay, combination of speed, the speed in a sense like the frequency, like transition frequency of your device. You can do power analysis, like how much for let's say for a transistor, you can how much peak drain current you can go at the maximum, density, breakdown, leakage, luminosity means like how much light it can generate, how much wavelength, how much intensity it can generate. So all those analysis we can perform. So some interactive tools. So the interactive tools, which are mostly graphical user interface, to create the structure, to characterize the structure. So mostly it's a graphical user interface, and so very easy to understand. User manual was also provided, so you can easily understand that. So some tools, the main tool is which is called DeckBuild. So it's an interactive runtime environment. So which is around 90% of the time you will be work on the DeckBuild itself. Okay. So whatever your input, like creating a structure, biasing conditions, adding a method, a model, all those things will be done on DeckBuild itself. So MaskView is for integrated layout editor. Okay. So some people have the layout file and they want to develop the layout file in a TCAD, so they can do it in a MaskView. So DevEdit and DevEdit 3D is for a graphical user interface structure editor. So basically it looks like a paint environment. Okay, you can just click and drag and draw your structure and you can do the simulation. So TonyPlot and TonyPlot 3D is a visualization tool. Okay, so whatever the structure is created, you can visually see that, or whatever the electrical characteristics and the characteristics it was extracted, you can visually see and observe it. So now we will directly go into mixer mode simulation. So you can see here mixer, which defines as circuit and device. Okay, so it will combine both circuit and a device. So some introduction about mixer mode. Okay, so the mixer mode module is a module of device simulator, which is Atlas. Okay, and it uses independent physics-based model, and along with the SPICE circuit module, and it will as a final, it will give you the circuit performance of your device. Okay. So to quickly tell you how this is like, that you have a transistor and you want to put it in this transistor. How much this transistor you want to make an amplifier circuit, and you can extract its the circuit performance. This is what the basic of the mixer mode. And so we cannot full-fledgedly go for a mixer mode circuit simulation, because there are some limitations with the mixer mode, and it has features also. So the features we will see first. The first is ability to link any mesh devices into a SPICE circuit, which means like so the device can be done on process simulation or device simulation. You can link that into a SPICE circuit, or multiple devices you can do, like let's say one is transistor, one is diode, okay, or another is some solar, like photodetector, something. So these three different devices you can include in a one circuit and get the circuit performance. And here you can perform DC analysis, AC analysis, transient analysis, okay, and all those things. And the mixer mode circuit, for a single simulation, the single circuit can include up to 200 nodes, 300 elements, and only 10 mesh devices. So this is what the limitations of the mixer mode. And you may ask what we can do for more devices. Okay. So there is another tool which we call it as EDA tool. Okay. So in a Silvago, which is called a gateway. Okay. It's basically like cadence environment. So if people work with cadence, okay, so it looks like a cadence, and you just need to let's say you simulate a TCAD structure that you will be taking it from a library and place it. So it has no limitations. You can go up to n number of so big circuits, all those things we can perform. So as discussed, so these are the two approaches. Okay. So one is, you can see right hand side and left hand side. Right hand side is an easy way. We can directly go to mixer mode simulation and get the circuit performance. The left hand side is like you go to EDA part, okay, and you can do the circuit simulation. So for that, different processes there. First is first you have to do process or device atlas simulation, and the parameter extraction you have to do, because the EDA tool will not directly support the structure file. Okay. So what we have to do is we have to do parameter extraction. We have another tool which is called Atmos 4. So this Atmos 4 tool will basically extract the parameter using different models like DSIM4, okay, and ASM models, FinFET model, okay, like a different model it uses, and it will extract the data and give it to us circuit simulation. So then after we will perform the circuit simulation and get the circuit performance. So mixer MOS is basically a easy and simple way to get the circuit performance. So this is the mixer mode flow. So first we just create one device, okay, so whatever the device we need, a transistor or whatever it is, and so once you have the device, you have to write the netlist. So netlist is very simple, how the circuit it should be. Okay. Let's say the device which has the circuit which includes resistors, capacitors, okay, and different inductors, different components. Okay. So these things, how we can convert that circuit into a scripting. Okay. So it is very straightforward netlist. The netlist writing is very simple. So we'll learn about that. Okay. And the physics model to work. Let's say you made a NMOS transistor. Okay. So for that we required a physics, right? Physics model. So on those cases you can use a physics model, and you can add an initial solution, biasing condition, and you can get the circuit performance. So these are circuit elements which are supported in mixer mode. Okay. So what is the circuit element is? Let's say you have a transistor and you don't have a resistors, capacitors. Okay. So those things you don't need to design again. Okay. So these things which are freely available in the mixer mode library, you can directly call that and you can use that. So these are some circuit libraries. Okay. So first one is it's our device, okay, and the second one is user-defined two-element device. We have to make it conditions. We can set the conditions. What will be the input? This will be output, like that. And so independent current sources, and the fourth one is independent voltage source. So these are different input elements like voltage controlled voltage source, current control voltage source, voltage control current source, and current control current source. So the next is lossless transmission line. Okay, if you want to use this lossless transmission line to observe its characteristics, you can perform resistor, capacitor, diode, and coupled inductors, And the active devices, which include diode, JFET, MOSFET. So in the JFET and MOSFET, that includes both N-type and P-type. Okay. On MESFET also N-type and P-type, and BJT also NPN and PNP. And the finally, which is optical source. Okay. Optical source, which is basically like you are doing some photodetectors, okay, and for that you need to give an input source as a light, right? So in those cases, you can use these optical sources. So the next is, so directly we'll just look into it, the syntax, okay, and the basic syntax. So the first thing you need to look into is, the first line is go atlas. So whatever if in a mixer mode mainly, you are start to work with this, okay. So the framework which we have to call is the device simulator framework, which is Atlas, okay. So for that, at the initial step, you have to give Go Atlas, okay. Or if you are working on an advanced simulator like Victory, you have to give Go Victory device, okay. So just remember that. And always if you are going to write a netlist, okay, it should be starts with dot begin and dot end, okay. And we can see what is this dot begin 3D, okay. If the circuit contains 3D structures, okay, so it should be dot begin 3D. So these are different special statements, okay. You can, so this dot model is for compact device models, like dot log, dot save is for saving output files, different output files. Dot node set, dot IC is for doing some initial condition settings, okay. And dot load is for initial condition. You can save it, you can save that using dot save, and you can call that and you can use it again, okay. So it will basically saves the time of the simulator. And dot numeric and dot options is for like you can choose the method, or you can choose the iteration, what iteration it should be used, whether it's a Newton method, Common method, or whatever it be. And so dot print is for device parameter outputs. Okay. So the like electron concentration, okay, energy band profiles. So all those things you can save it in a structure and you can visualize that. So dot options is for like additional things, like you want to include the thermal behavior, okay, or whatever. So additional things you want to include in your structure, in your circuit, you can give dot options and followed by some syntax will be there. So now we'll just directly go to writing how to write the netlist. Okay. So basically I'll go to the next slide. So this is the circuit, the basic circuit I'm going to write a netlist, and I will explain you how to write it, how to write this netlist, how this netlist works is. So going to the before slide, and so let's consider for this circuit, the diode is basically a structure file which will be created with the Atlas structure file. So basically, like the diode we have created, our device, okay, and the resistor and the voltage source are a circuit element, okay. So now to save, to load our device, like in our case, which is a diode, okay. So the mixer mode syntax, the first letter defines everything, okay. For example, the previous slide I'll show you. You can see, for example, resistor means R device are given, capacitor means C device, diode means D device. So basically, the syntax is R. For resistor, the syntax is R. The capacitor, the syntax is C. Diode, the syntax is T. The first letter defines what you are going to write. So what the device it should be. Okay. So for example, for first thing is A, which is an Atlas device element. So Atlas device element, which which is a diode. Right? So the diode, how we can include that, which is the first letter, it should be A. Okay. If it's an our device which will be created in a process simulation or device simulation, it should be the first letter should be A, followed by that XXX. So which basically like user defined. So any name you can give. Okay. Like you can give diode, okay, or any name, like your own identification. It won't, the simulator won't include this. Okay. And followed by that node. So N1 defines nodes. Okay. So nodes means, so for this circuit, okay. So you can see here the resistor, that two dots are connected, right? So these are called basically nodes. So these are nodes. These connecting wires. So N1 equal to electrode name, okay, and N2 equal to electrode name. So if your device has how many electrodes, you can give as per it is. So if your device has 10 electrodes, you can provide as per it is, okay. And along with this, I have given in the syntax, you will see the square bracket, right? The square bracket, which defines it's not compulsory. So if you don't provide it, it will take a default value. So just remember that. And once you've given this nodes and the electrodes, okay, and we have to tell where this structure file comes from, okay. So you can write in file equal to, and if you save it as diode.str, you have to give it, that file should be copied in the same directory, and you have to give diode.str, okay. And width, you can give like, so if you haven't provided the width, because it's in square bracket, right? If you don't give it in the give width, by default it will take 1 micron as a default. Okay. So you can give accordingly. So width is basically like, let's say you created X and Y 2D structure. Okay, you haven't defined the Z-axis, right? So that is what width is. Okay. And the conductor is like, this device will act as a conductor or whatever it is. Yes. Yes, yes. So for example, like you open a deck build and write a co-atlas and this syntax. So where you saved that document, no? So in the same directory you have to copy that diode structure file. Okay. So then only it will call that name and it will get that structure file. And followed by that, which will be a resistor. So to take the resistor, the syntax is the first letter is R, we already seen, and followed by that XXX is not only 3, you can write unlimited, like without space and without special characters. Okay? And also you can include numbers also. Okay? And plus node and minus node, where it should be connected, plus node or minus node, and the value of the resistor. So you can write it in ohms, or you can write it in, like, if it's a 10 kilo ohm, you can write 10k. Okay? Or if it's a 100 ohms, you can write just 100. Okay? So this is what the syntax is. For independent voltage source means the, so it's basically a DC voltage source, okay? And the first letter it should be B and followed by some name you can give. So this name should not be saved. Like previously you used this name and so again you should not use. Okay? So it should be different. And the plus node and the minus node and the initial value. So this is the basic syntax. So now we will directly write that netlist. How to? Okay. So for example, so begin with Go Atlas. Okay. Start with dot begin. Okay. And end with dot end. Okay. So these three lines are the mixed mode netlist. Okay. So this basically defines the circuit. So you can see here, so just remember this, first you just draw the circuit, okay, and for example, this connecting wires you have to name it yourself, okay, so here I am naming it as 0, okay, and for this node I am naming it as 1, and this node I am naming it as 2. So any name you can give, like you can give ground, or A1, B1, like this. Any name you can give. It should be like the same name you should not give. Okay? And so first this element I am going to write. So this is an independent voltage source. Okay? So first letter is B. Okay? And followed by that 0 is my identification name. Okay? So I am writing it as 0. Okay? Anything you can do. It's an input, right? So you can give input. Okay, and follow that plus node and minus node. So plus node is 1, minus node is 0. Plus node is 1, minus node is 0, and I am applying a voltage of 5 volt. Okay. So this is if you have any doubts you can ask. So the second line as usual same thing. R defines resistor and 1 defines user defined name, any name you can give, okay, plus node, minus node, okay, so the plus node is connected to 1, minus node is connected to 2, and resistor is bidirectional, you can write volt also, no issues, okay, and you can give the value of the resistor, okay, and our diode device, okay, A, and followed by that I am just writing it as my name, my own identification name, diode, okay. So 2 is connected to anode, 0 is connected to cathode. Huh? No. So anything you can write, no issues. And width I am giving 10 for my device, and in 5 I am just writing it as diode.str. So this diode.str should be saved in the same directory. So this is the base, the basic. So this is I haven't done simulation and I haven't done the diode.str created that. So I'm just giving you an idea. Width. It's a z-axis. Z-axis. No, for example, let's say you create a structure in 2D, right? So for example, let's consider this is your device, okay? So this is a y-axis, this is a z-axis, sorry, x-axis, okay? So the device will not work in 2-dimensional, 2D, right? So if it does not have a z-axis, the device will not exist, right? You understand? No. Marker or something like that. Yes. Board is basically a z-axis. I will tell you what is that. You see, which is a gate, and so in the top, which is gate, and source and the drain at the bottom. Okay, so this is a roping profile, and so initially to cover this, I'll just show you how to create the structure at the beginning. For examples, here I will give you complete details. I'll give you, and so we will look into it. Okay. So first, I'll just open a deck build tool. Okay, and just load that example. Okay, so here to give you an overview. Okay, so first the DMOS will be created. Okay, so how it was created is using a process steps. Okay, so the first thing is Go Athena, which we will be calling it to do the process simulation, and we will be so basically it will call all the process frameworks and process library it requires. It will call it that. Okay. So initially we have to provide the coordinates, the work area. Okay. For it, the line X will be start with 0 to E and to 10. Okay. Hash indicates it's a comment. Like if you write the hash and you can write anything. Comment. Like you can write anything and it will just ignore. The simulator will basically ignore that. Okay. Yes, yes. I will give you the code. You can just open and meaning flash drive, or I will just mail you. Now only I will give exactly flash drive. What's up?
हो गया दिखाओ सबसे आखिरी में हो गया दो अटेंडेंस है मॉर्निंग की अलग इवनिंग की अलग मेरे हाथ से अरे एक में और लिख दिया मैंने तो तुमने किसी में लिखा है
essentially part of the verification. 7 cent plus government
ये दो काम
plus government 7 cent.
ये क्या है
You got 2 certificates.
बताओ ना
One is to Manoj and one is Manoj. To Manoj Kumar.
मनोज कुमार को नहीं ये इवनिंग है ठीक है ये इवनिंग हो गया ये आ गया इवनिंग खत्म हो गया
नहीं वो भी evening.
ये इंटरनल होंगे
आप इंटरनल व्यू एक्सटर्नल व्यू
नहीं, मैं एक्सटर्नल था ना।
इंटरनल व्यू आपके
हाँ वही तो
दो
बताते हैं नहीं।
तो बस
अब मैं बताएगा जल्दी तो कोई
हाँ शनिवार तक पूरी करेंगे।
So first thing is we just explore the tools. Okay. So the first what you are seeing is basically the tool which is called as Build, and here is where you write all the scriptings. Okay, like to create a structure, or you to create the structure, or adding some process steps to create the structure. Adding models, netlist, biasing conditions. So whatever the user data, you will be writing it in this netlist itself. Okay, and so you have to write the code here. Okay, and also there is another way to write the code, which is called graphical user interface. To write the code, to do this, you can just go to commands. Okay, syntax dialog. Okay. And you can choose whatever it is, like process simulation or device simulation. Okay. So if it's a process simulation, you can go for initially mesh initialization. Okay. Let's say you want to deposit certain material. Okay, after different thickness. Okay. So once you choose the materials and its thickness, you just select the line and give write. It will write the code automatically. Okay. So likewise also you can do. And so whatever the files will be created. Yes. So if you are very new to this and you want to use this command, you can use, and if you are familiar with this, you can directly write. No, actually, in one of the this script, this is not basically a scripting. So this is like directly like English, for example, you want to deposit some material. So what you write is deposit silicon thickness equal to this value. That's it, right? So that is the syntax. Okay. And you want to etch some parameters, etch, and what type of etching it should be, like dry etch or like wet etch. You can write dry etch, and its coordinates you can choose. It will etch. So that's it. That's the syntax. Okay. So it's very easy to learn and very easy. Okay. And so this area is basically called variable history. Okay. So variable history is basically used to extract the different parameters. Okay. We have different extract parameter examples. Like if you go to the commands. Syntax dialog and extract dialog. Okay, so you can extract different parameters. In the device threshold voltage, you can extract the theta value, theta, leakage current, subthreshold voltage. Okay, from the electrical characteristics, you want to extract those values. You can use those commands and you can just write it. So whatever the once you do the simulation, no? So whatever the subthreshold voltage value, it will be displayed over here. Very simple. Okay. And not only for device and also for process simulation. So process simulation means material thickness. Okay. So different material thickness, junction depth, sheet resistance, sheet conductance. So different parameters are there. You can just choose it and it will just basically extract the values. So that's where the variable history comes. And output files is basically if you save whatever the files which is generated by your code will be displayed over here. You can directly launch that file also. So for example, so this is the file. So I just right click and plot it. So this is the final vertical TMOS structure. So you can see different things like doping profiles. Okay? Doping profiles that include like different concentration, like boron concentration, phosphorus concentration, or like you want to see it in N-type and P-type net doping profiles. You can choose net doping profile. You can see it in N-type and P-type. Easily you can visualize. And you want to take the cut line. Okay, or like you want to see the certain one-dimensional plot, you want to see its concentration, you can do that. So you can go to tools, cut line, okay. So vertical or horizontal cut line you can choose. So let's say on this area I want the profile, okay, just click and drag. Okay. This one-dimensional part will be displayed over there. So you can do lots of So I'll just plot this again. So you can, to plot this, you can directly okay. So this is the structure. Okay, so initially I have told you about the sampling, we call it as meshing. So for, let's say we created this device, okay, and it will, okay, so starting from the beginning, okay, the Tony plot can visualize its it's a space on meshing, how the meshing will be created. So for this you need to go to right click display and choose the first option, which is mesh. So if you choose this, so you can see your device is filled with triangles. Okay, so these are we call it as meshing. Okay, so in these triangles, the electron transport equations like diffusion, Poisson's equations will apply. Okay, and we will extract its electrical characteristics. Okay, and so we can choose how much meshing it should be created. Okay, like for example, if you reduce its thickness, reduce this size, it can able to accurately predict the electrical characteristics. Number of the mesh will be more, but the effect on this is the simulation time will increase. Simulation time will increase. So, for example, for this type of mesh, the simulation takes around 1 minute. If you want to increase its accuracy, and if you want to increase this, it may take more than 1 hour. Okay, if it's very dense, it may take more than 1 hour. So you can design how much mesh we have to give. Okay. Yeah, it's up to you. You can give different meshing. Yes, for example, let's say for a normal MOSFET, okay, let's say the normal MOSFET, the silicon bulb will be there. Okay, in the top, there will be a channel area. Okay, you know that this is where the channel area. So you can give in that area only dense mesh. In other area, you can give the bigger triangles. Okay, so in those way you can accurately do the simulation, and at the same time you can reduce the simulation time. So first thing is like, so I have taken this example, okay, so which is this DMOS, vertical DMOS structure is created with process simulation. Okay, so which is Go Athena, and so I'll just directly go to the mixer mode. So I'm just giving you a basic idea how to create and how this things works. Okay. So initially, like this is a meshing profiles like x coordinates, y coordinates, and how the spacing it should be created. Okay. So this is like initial deposition of silicon. Okay. And epitaxy deposition of different materials, etching. Okay. So they are doing some different etching, and they are doing the implantation of boron. Okay. And and also they are etching the photoresist layer, diffusion process, implantation process. So after different process steps, right, like etching, diffusion, implantation, okay. So we get this final structure. So this is what the structure it is, okay. And so now I just directly go to the mixer mode. So this is the mixer mode code. Starts with Go Atlas. Okay. So if you are performing a process simulation, you have to go Athena or go Victory process. Okay. So Victory process is basically advanced process simulation. Okay. So it's based on what license you take. And if you are working on 1D device simulation and you want to perform the device, extract the electrical characteristics, optical characteristics. So these are all comes under device simulation. So you have to call Go Atlas. Okay. So we start with Go Atlas. Okay, and you can see here this is the circuit definition. Dot begin. Okay, and finally ends with dot end. So in between there is lots of biasing statement and syntax which are included. I will explain that. Okay. So this is the initial guess. Okay. So in the yes. So I will explain you that, sir. So before that, I'll just giving an idea. Okay. So once you have done this simulation, okay, you can give dot end, and so here this is for physical models and physical your device, some parameters. For example, contact. Okay, you are choosing it as gate as an N polysilicon. Or in your case, you can choose work function, or you can use different material. Yes, metal. Yes, you can. Yes, you can choose. For example, if you are choosing a gold, you can choose work function as 5. So you can just work equal to 5. Okay. So likewise, you can choose accordingly. Okay. Yes, you have to write it sequentially. So this, if you, yes, the simulation also will run sequentially, line by line it will run. Okay. And the interface charge you can give, and the models to work with it. Okay, like the CON-MOB, FLT-MOB, concentration dependent mobility models, field dependent mobility models. So these are the basic things, right? And for a HEMT, so it works in the basic of some kind of polarization effect, right? So spontaneous polarization effect will happen, 2DEG will happen. So in those cases, you have to include polarization model plus mobility model and SRH model. So likewise, you have to choose it. Yes, as per the physics. Yes. So we can use Albert and so we can use both spontaneous and piezoelectric. So I will just check and I will update. And once you choose those models, you can do. So this simulation is basically like they are performing type of thermal based one. Okay, so they are choosing this impact ionization, which is Saber model they are choosing. And the method they are choosing iteration as Newton, and auto-NR is another iteration method, and they are including a drops. So once you simulate this, you will get the circuit performance. Before that, I'll just go for this presentation, and I will explain you the netlist. Okay. So initially you have to create your structure, which is a vertical DMOS structure that can be done in a process simulation. We have seen that. Okay. And the next step is like writing the netlist. So to write the netlist, okay, this is first the circuit you have to. Okay. So first the circuit you have to draw it in your notebook. Okay, and you have to name the nodes. Okay. So for example, this entire node I am just named it as 0. Okay. Ground. You can name it on your own. Okay. You can give 0, 1, 2, 3, 4, whatever things you can give. Not only numbers, you can give GMT, ground. So without space, you have to. Yes. No. So ground is not a syntax, no. No, it's not like that. It's up to you. Whatever name you can give. No, for this node, for this node, whatever name you can give. Number or name you can give. Okay. So I am here and named it as 0. Okay. And you should not use different same name for a different node. So I am naming it as 0 for this. And for this node I am naming it as 1. And for this node I am naming it as 2. And this node I am naming it as 3. Okay. So now to begin with, which is I. Okay, this which is a current, independent current source. So independent current source, we see that the first letter defines everything. So for independent current source, the first letter is I, right? And followed by that, in is a user-defined name. Any name you can say. In you can give, input you can give. So whatever things you want, you can give. Okay. 0 defines plus node and minus node, right? So plus node is. So it's connected to 0, minus node is connected. So it's opposite way is connected. Okay. And the initial value, which is 0. So initial value of the current is 0. So later part we want to include. So basically we want to include a pulse input here. So for this we can write as pulse. Okay. So there are not only pulse you can give. Okay, you can give sine wave, sinusoidal wave. I'll show you this in a user manual. I'll just show this. You will get a better idea for this. So if you go to this 13.4.3 user manual, which is a transient parameter. So the first one is an exponential waveform you can do. So you just type exponential, and these are the explanation like initial value, pulse value, delay time, and so on. And you can do Gaussian waveform also you can provide. For Gaussian, you just include as Gauss and Gaussian waveform. And for our case, it's a pulse. Okay. So we are giving a pulse waveform as an input. Okay. So for the syntax is pulse. Okay. Initial value. Okay. And peak value, delay time, rise time, fall time. Okay. And the pulse length and the period of the pulse. And Apart from that, you can use piecewise linear waveform. Okay, and you can choose the piecewise linear waveform which will be saved in a file. If, for example, people they do some kind of analysis, physically they do some analysis, they extract this, the pulse waveform file and they can input that also. And modulated sinusoidal waveform, okay, and table wise, like this will be different statement, like table wise you can write, so that also you can. So these are the different parameters as an input you can provide. So in our case, which is a pulse, okay, and so these are some parameters we have seen, like so initial voltage, pulse and initial voltage, peak voltage. Okay, so initial delay, rise time, fall time, pulse width. Okay, and the period of the entire pulse. So this you can give as per your requirement. And followed by that, it's an R. So now we just define, we have defined a current source, now we will define a resistor. Okay, for resistor, the syntax is R. Okay, and followed by user defined. One is a user defined, anything you can provide. Okay, so plus node and minus node. So plus node is 1. Minus node is 0. Okay. And you can give its value 1 e power 6. So or you can give it like yes, something like that, 100k. Okay, like this you can also do. So here they are given in ohms. Yes, they are given in ohms. So you can convert that into like if you write it in K value, you can write it in K. Or if you want to write mega ohm, you can just write M. So in ways you can convert that. So now the current source is. Okay. So the independent source is completed, resistor is completed. Now we just write the MOS, DMOS. So which we have already created using the process steps. Okay. So as usual, the syntax is A and followed by the user defined name. Okay. So there you will be saving it in the electrodes. Different electrode statement you will be given. That is gate, drain, and right. So these nodes where it should be connected. Okay. So where we can connect this gate will be connected to 1. So 1 equal to gate means gate will be connected to 1. Okay. So 2 equal to drain means drain will be connected to 2. Source is connected to 0. So like this we can connect all the electrodes. Yes. So this if you give 5 and equal to and whatever the name you saved it there, okay, the same name you want to provide it here. Okay. And it should be, the structure file should be there in the same directory. Okay, that you should remember. So the name .str, it should be saved if it's this is basically a case. Okay. So if it's changed, it won't be taken out. Okay. And you can give the width, the z-axis. So if this width is not provided, by default it will take 1 micrometer. So this is done. Okay. As usual, you can give current out also. So current out, I out, and the plus node, minus node at the value. And for diode, you can choose D. Okay. The syntax is D followed by user defined name, plus node, minus node, and the model name. Okay. So model name I have given ideal. For your case, you can write whatever name you think of it, you can write. Okay. So for example, you can write a demo or test, training. So whatever it is you write. So later part you have to call the same name. Okay. For example, the bottom part, the dot model, the same name you have to call it. Okay. And you can write it as D. D key and bracket if you put, it will be take it as a diode. So if you are calling it as for a MOSFET, you have to write it as NMOS or PMOS here. So that we will see in our examples. Okay. And as usual goes for the V. Okay. So the V is like 3 and 0, and the voltage is set as 20 volt. Okay. For this balancing condition. So if you have any notes. So yes, yes, we have a training video. If you want, we will share. Yes, we will share. So, actually, for the concentration of 1/16, and to make this doping profile here for N-type and so it's here it's an N-type and here it was a P-type, right? So in P-type there is some kind of you can see some kind of Gaussian type of profile is there, right? How the electrode will form now is one dimensional. Okay, just so I will show you that in the structure. It just places an electrode in that, like it was a contact. So this is for doping. So initially P-type doping they are doing, and second the Gaussian profile they are doing for the same P-type. So this char and peak they are giving, okay. So which means the initial state will be 0.2 and the peak will be 0.15, which will be like we are performing a Gaussian profile. So at the rate of step from 0.2 to 0.15, at the rate of step, it will the Gaussian profile of the P doping will be created. Okay, and here the P type will be made for entire structure. Okay. And for here they are performing an N type. Okay. N type here they are making a junction. Okay. So junction is equal to 0.17, which means so at so junction means which we can take it from y coordinates, okay, from 0.17, from 0 to 0.17, okay. So there will be one junction will be created, okay, and along with that x right hand side, x dot right equal to 1 microns, which means it will be up to 1 microns x side, it will be create one junction, okay. So this area will make the entire dopant, okay. So this dopant ratio, the Gaussian profile ratio we can change. So they are giving 0.7, okay. And if you want to increase the Gaussian profile area, so you can increase this ratio. So we'll change this ratio and we'll see that how it has been done, okay. As well as go for the N-type. Two junctions are there, two N-types. So initially it's a P-type and there is a two N-types under different regions.
ऐसी क्रॉप कर रहे हो क्या फोटो तुम आजकल, क्या चल रहा है?
डर लग गया
डीफेक सिस्टम करते हो?
है, डर लग गया बाबू।
So the structure creation is done. So now we will go for a circuit simulation. Okay. So for this device we will do a circuit simulation. So to do this mixed mode simulation, so in the previously we have seen how to do it. First thing is we have to get an initial guess. So let me scroll behind. So you can see here, first you have to create the structure and make a netlist physics model. And the main thing is first you make an initial solution, okay? And then we will be performing a DC simulation and transient simulation. So this is an important thing, okay? So first we'll do this initial solution. To do initial solution, as usual, we have to write the netlist. Okay? So to write the netlist, okay. So this is the netlist. Okay. So just writing it. Okay. Give me a moment. So this is the circuit, and we have to make different names for the each nodes, right? So it can be for a ground. I have named it as 0, and so here it should be 1. It's in black color. And for this node, I'm making it as 2, and this node equals 3, and this node is equal 4. So you can do it. You can write it like VCC, ground, input, output. So whatever you want, you can write. Okay. So first thing is the input I'm going to identify. It's an independent voltage source. Okay. So the syntax is V. Okay, followed by user-defined name, plus node, minus node, and the initial value. Okay. So plus node is 1, minus node is 0, and the initial value will be 0. Because this will be our input, I'm going to sweep from 0 to 5. Okay. So while sweeping, we will make it as an input, and we will see whether how this we are getting a transition and all. Okay. So if you have any doubts on this, no, right? So moving to the next part, this is our device. Okay, this is our NMOS device. So for our NMOS device, what we have created, the syntax will be A, right? So the first letter will be A. I'm writing it as N. Okay, and we can write any user-defined names. Two node is connected to drain, right? So drain. 2 node is connected to drain. So 1 is connected to gate, and 0 will be source, and 0 will be equal to substrate. So you can see gate is connected to 1, drain will be 2, and source will be source and substrate. I'm connecting to 0. So substrate I'm connecting to 0 because it's an NMOS. It will be pulled down, right? And followed by that, we have to give the in file. Okay. So in file equal to, and the structure name we have saved it. Right? So previously we saved that structure as nmos.str. So we have to give that nmos.str. And finally we'll give width. So width of this device will be 50 microns. So if it's not given, so it will be taken as 1. So the width will be optimized, okay, for this circuit. Okay, you can optimize it for your purpose. And followed by that, this is a device will be taken from a library element. Device define a MOSFET, okay, and then defines user defined as usual. So drain, A, node, and source and substrate. So you just name that wherever it connects. And simple I'm giving it's a model name. So later we'll call that model name and we will tell that whether it's an NMOS or PMOS. Okay? And some other value also will just tell. So initially length and width of a channel. So length will be 2 microns, width will be 5 microns. As usual goes for the resistor R and user defined name. So 2 and 4, you can say 2 and 4, and for the value will be 10K. R2 will be 3 and 4 and 10K. And finally the capacitor, okay, you can see that capacitor syntax will be C and the user defined name as 1. 3 plus node, negative node is 0 and 3 femtofarad. And once the circuit is created, we have to apply a supply voltage, right? So you have to make a supply voltage. So for that, V, independent voltage source, and the CC, our identification, 4, 0, and the 5 volt are just setting it. So if you have any inputs on this. No, nothing is not.
और राम मिश्रा तूने असिस्टेंट रखी है असिस्टेंट रखी है तूने
क्या
क्या ये मैटर तू ठीक इसकी ना मैशिंग ठीक से
ठीक है अच्छा डिजाइन
Actually, how to access the user manual, I'll tell you. Okay, so just type go address from the tool itself. You just type go address, right click on the tool, and you can choose open address manual. Okay, it will launch the complete manual details. Okay. So the complete manual is there. The mixer code will be there in the chapter 13. So if you go to chapter 13, the completely so whatever things required, you can easily get that. So using of the mixer mode. So general syntax, you can directly read it from it. So the same thing I just copy pasted here, okay? And so this simple, we will be calling this model, okay? So here we have written dot model, okay? And the same name you have to give. Okay? So if there you have given some MEID, same name you have to give, and you have to tell that what device it should be. This is a syntax, okay? It should be an NMOS or PMOS. If you are calling a BJT, it will be NPN or PMOS. It's based on that. Okay? And you can provide some other parameters, oxide thickness, threshold voltage. Okay? So these things you can provide. So for example, let me show you this. Other parameters are there. For example, or for MOSFET. Okay, so this is where you will find this model statement, and you can, so different parameters are there, you can change that. thing is, so dot numeric and V change equal to 1. So this parameter is basically like, so we will be making additional things like we are setting certain condition for the simulation to make the simulation easier. Okay. So V change is basically a voltage and is full Newton method. So it's a complete profile. The standardly available Newton method it will take to do this iteration. So full N and motion. So now I'm just loading that previous file. Okay. So you can see here. So previously I saved that .mos. So now I'm just loading that file. Dot load in file equal to mos. Okay. And so now I'm saving it in a log file. Okay. So in Silvercove, the structure will be saved. It will be saved as .str. And any electrical characteristics, optical characteristics, right? It will be saved in .log file. Okay. So to do that, we have to give .log out file equal to some name. Any name you can give. So here I give mos2x01. Okay. So based on that, it will be saved. Okay. So now we will be doing a biasing condition. Okay. To do the biasing condition, so you can see this is the input. Okay. So this is the circuit element we will be providing it as an input. Okay. From 0 to 5 volt we will be sweeping it. Okay. So we just calling this in DC simulation. Okay. So just writing it .dc. Okay. And B. Okay. And initial voltage is 0. So previously we have given the voltage will be 5. Okay. And the step voltage will be 0.25. Okay. So what will happen? So initially 0 voltage will apply and it will simulate, and again it will apply 0.25 and it will simulate, and plus 0.25 which means 0.5. Okay. So likewise it will step until 5 volt. Okay, and it will simulate. So now we will see its graph. Okay. So this is what the DC curve. So let me plot it. Okay. So initially it was just a line. Okay. We can see here in x-axis it was V1. V1, what is this V1 as? It's a node 1, voltage on node 1. Okay. If it's an I means current on node 1. Okay. In the y-axis it will be like I capacitance. It was showing the capacitance. So we just remove this capacitance value, current of the capacitance. So to do that, what you have to do is right click, display. Okay. You can see what will be the x quantity and what will be the y quantities. Okay. So x quantity, I'm just giving 1. Okay. So 1 is an input. Okay. And in y quantities also I'm choosing 1. Okay. So y quantity you can see, I think it will be visible. If it's not visible at the log. So it is V1. Okay. So which means x quantity also V1 I'm choosing, y quantity also V1 I'm choosing. Which means input versus input. So we can see what will be the input is. Okay. So you can see here, basically the voltage is ramped. Right? From 0 to 5 volt, the voltage is ramped. Okay, at the step of 0.25. Okay. So this is the input. Now we will see the output. Okay. So if we go to the circuit, so 1 is an input and 2 is an output, right? Output node. So now we will select a V2 and we will visualize it. Okay. So right click, display. So V1 is already selected. So now we will select V2 and give apply. Okay. So you can see here, since it's an NMOS type of transistor, so initially at the time of at the lower voltages, the device, the output is at on state. Okay. So once it reaches its threshold voltage and device turns on, okay. So suddenly you can see the drop, okay, and it's turned off. Okay. The first inverter is working. Okay. So now what we'll do is we will see the second inverter. Okay. the second final output will be 3, right? So note 3. So we choose V3 and give OK. Okay, you can see here. So we are getting an inverted output. So the blue one is a final output. So you can see it was inverting it. Okay, whatever the input we are giving, we are getting a same. Okay. So this is the red one is an input. Okay. So we are getting a same one. So this is the DC simulation. If you have any doubts on this, please ask. Huh? Yes. So, any doubts? Yes.
पीने का पानी
And I will share
पीने का पानी है
this code.
पीने का पानी
You can run that and see that also. Okay. Or else you can directly take this code. It's already available in the example. Okay. So if you go to File, Examples, okay, the technology session, you go to MOS example. MOS example, MOS, I think MOS 2. Okay, the first example, which is a circuit analysis of NMOS inverter. Yes. Yes. So you can see its characteristics and all those things. You can load it. Okay, you can see that. I hope you understand about the DC curve simulation. So now we'll see about the transient simulation. Okay. So the beginning, so followed by that, the transient simulation has been made. Okay. So as usual, the same thing. Okay. So instead of giving ramping voltage, input voltage, so what we will do is we'll just give a pulse input. Okay. For a transient analysis, we'll give a pulse input, and for transient analysis, we'll give some certain time, starting time and ending time, so that we'll get a transient response. Okay. So you can see here. So in this statement, we will be writing it as pulse input. So not only the pulse is limited, so you can apply different signals like waveforms, like sinusoidal wave, exponential graphs, and so on. So here are this pulse we are giving it. So these are the values, parameters of the pulse. Okay. So this what will be these parameters? You can easily find it in a manual. So let me show you that. Okay. So if you just go to MOSFET, pulse, right? The transient parameters, it will be there in the 1343, and you go to select a pulse. You can see here what will be the each statement. You can easily go through it. Okay. So rise time, fall time, and so on. So 0 will be the initial value and the peak value of 5. Okay, so 0 and again third value is delay. Okay, 50 picosecond is a rise time and 50 picosecond is a fall time. 100 picosecond it will be the pulse width. Okay, and 10 will be the pulse for a single pulse period. Okay, and as usual same thing. So here you can see instead of dot DC we are giving transient. Okay, so dot tran. So we can give 0.001 picoseconds, which is the final transient time period. Okay, and this is step. Okay, and you can give dot 10. Okay. So now I'll just show you this transient graph. Okay. So initially it's on transient time on the x-axis, and you can see some capacitance. We change that. Okay. So right click display. So I'm just removing the capacitance at the beginning. So one is an input. V1 is an input driver. So I just select one. So this is the input pulse we have given. Okay, so we have made it right. So initially it will be 0, the lower it will be 0, the peak will be 5 volt, okay, and there will be no delay for the pulse. Okay. Rise time is 50 picoseconds and fall time is 50 picoseconds. The entire pulse will be like around 1000 picoseconds, like that we have provided. Right? So this is an input pulse. So now we'll see the first inverted output, okay, which is V2. Okay, so you can see here the first inverter output is a green one. So when the pulse is high, it comes to 0. Okay, so when this pulse becomes 0, so it again switches to high. So this area you can analyze like delay due to RNC, okay, and the final graph also you can see by V3 and can be okay. So you can see here we are getting a non-inverted output, but we can analyze its delay and so on. If you have any doubts, please ask. By continuation, you can play it. You just write that. Yes, yes. Yes, that is also done. Can be done. Yes, same folder. Yes. So, any doubts on this transient analysis? So, shall we proceed?
क्यों? अरे कौन सा लाइव चल रहा है वो देख रहा है इसमें क्या कर रहा है यार इसे कहते हैं क्रिएटिविटी अभी तो शुरू होगा टेस्ट है अभी टेस्ट लेगा तो मैं जा रहा हूँ हाँ सुनो भाई अरे यार मेरे को भी निकलवाना कभी निकलवा के आऊँ बड़ा क्या है ऊपर से शीट नहीं है बहुत सारी जामुन को दे देते हैं जामुन शीट मिल जाए ऊपर निकल जाए
Understand how the spacing works and how to view the spacing. So I'm giving it as 0.1 and 0.1 for both. Okay. So if you give 0.1, so 0.1 is basically 100 nanometer. So it will be splitted. The total of 1 micrometer length will be splitted 100, 100, 100, which means 10 splits it will be doing. Okay. So now we will be defining a Y mesh. Okay. So to do this, we just type the syntax which is called Y dot mesh. So because we have to provide two points for 2D structures. So we are seeing the 2D structure. Later I will show you how to do it in 3D. Okay.
आगे से खींचना क्या आएगी बिना खाए निकाल मार
So you can see here in the Y mesh I am giving a location starts with 0 to 2 microns. Okay. And the spacing I am giving as usual. I am giving an 100 microns, which means it will be at 20 splits. Okay. And I will tell you how to optimize that, how to give dense mesh inspecting area and all those things. So now the work area is done. So work area means x-axis starts with 0 to 1 micron and y-axis will be starts with 0 to 2 microns. So now we will just add materials. To adding the materials, you have to create a statement called region. Okay, so the syntax I just wrote, the first thing is region, and region number you have to provide, region number equal to 1, and material equal to silicon. Okay, so if you write like this, so what will happen is for the entire region, the entire coordinates, whatever we are given, whatever the so the work area is created, it will be filled with silicon. Okay. So now I am going to save this structure and we will be visualizing it, how it looks like. Okay. So the command to save is save outfile equal to some name dot str. Okay. Okay, so this should be to save out f equal to test.str. So you can write whatever name you want and it should be saved as .str file format. Okay. now I am saving the code. So file and save. So I'm giving some name. Test1.in. It should be saved as test1.in. Okay, test1.in and save. So once you saved it, you just run it. That's it. Okay. So I think some resolution changes is there. So give me a moment. Okay. So now to open the structure, so what you have to do is you have to right click this test.str and give plot test.str. So right click on the test.str. So this place a cursor here. So right click and plot. That's it. So the second option, plot test. Okay. So you can easily visualize this, the structure. Okay. So you can see here x coordinates it starts with 0 to 1 microns, and the y coordinates you can see 0 to 2 microns. And so you can visualize your meshing. Okay. How to do this is right click and go to display. Okay. So right click and the first option is which is display. Right click and the first option is display. Okay. And select the first option, okay, which is mesh, and give OK. Okay. So the grid will be formed accordingly. Okay. So now you can understand how this meshing works and how to give the meshing. Okay. So now we will optimize this meshing. Okay. And so if you have any doubts and if you face any difficulties, please let me know. I will. Okay. So now what we will do is we will change the spacing and we will see. Okay. To change the spacing. So before that, let me previously we discussed. Let's consider this is a channel area, and we want a dense mesh on this area only. Okay. All other ends we need a basic mesh. Okay. So to create a basic mesh, let's say. Just think of it from starts with 0 to 0.2. Okay. So just add 1 point there. Okay. So what I'll do is just copy this line. So from 0 to 0.2, I'm adding one more line. Okay. 0.2, and now I'm increasing its spacing. Okay. So I'm giving 100 nanometer to 10 nanometer. Okay. So in this area only, okay, from 0 to 0.2. So now we just run it and see. Okay, the simulation is done. So what I'll do is right click this. Now I'm giving plot append. So if you give plot append, it will show in the same Tony plot. Okay. So you can see here the same Tony plot. Now I'll show the mesh. Okay. In this area we are given a dense mesh. In all other area it was a loose mesh. Okay. I hope you understand this how it works. So, if you have any doubts on this, please let me know. So, no doubts, right? So, we continue. Okay.
Yes, sir.
So, the 2 points I have changed. Okay. Yes, you can see here, after 0.2 also it was a little bit dense mesh because, so the code will automatically do this type of things, okay. So it will try to optimize its grids. So basically ma'am, we make yes, so why it's creating like this is, if it was created like that, it may face a convergence issue. Okay, at the time of the calculation of the electrical characteristic, it faced some issue. So for that, it tried to optimize it. Yes, yes. And same thing goes for X also. Okay, X also. In between areas you can add and you can add dense mesh. For example, the center point, let's say gate will be there and channel will be there. So in the center point, I'm just adding one more layer to give a dense mesh. So we'll see that. So the center point will be like around 0.5. So you can give whatever you want. So I'm giving 0.2 something like that, or 0.1. Okay. So I'm running it. Okay. So once it's done, just plot it. Okay, you can see the difference. Okay, in this area it was dense, in this area it was dense. So based on like that, you can optimize this meshing. Okay. And I hope you understand, and I'm continuing with the next step. Okay. So the next step is I'm going to add an oxide region. Okay, gate oxide region, and I will show you that how to do it. So the number defines region number 1. Okay. So the second region I'm going to add, which will be an oxide layer. So I'm just writing region number 2 and material likewise. So here I'm making it SiO2. So here you can see initially for silicon we haven't given any coordinates, right? So if any coordinates is not given, so the entire region it will just fill out. The entire work area it will just fill. Okay. So now this oxide region we want in only the top layer. Okay. So what I will do is I'll give some coordinates. Okay. So for this to give a coordinates you have to give x minimum, x maximum and y minimum, y maximum. Okay. So I have written a syntax which is x dot minimum and x dot maximum. Okay, so minimum is basically a starting point of x, and the x maximum is the ending point of x. Okay, and as usual goes for the y minimum and y maximum. So now in the structure, so for example, for x it will be like starts with 0 to 1. Okay, so I'm giving 0 to 1, 0, and the ending point will be 1. Okay, and for y. So I'll remove the mesh so that you can clearly see. So now I'm giving the y will be 0, okay, and the y max I'm giving it around 0.1, which is 100 nanometer I'm giving. Okay, so just for this demo. Okay, so now I'll just run it. Okay, so now I'll just plot this. So you can see here the SiO2 will be formed. So if you have any doubts, you can ask. So any doubts, right? So moving to the next step for this MOSFET, so we will just make an electrode. Okay, so the electrode will be source, drain will be here, and gate will be in the center part. Okay, so to do this, what we have to do?
हमने उसको मिसिंग अपने नहीं दिया।
So now we'll create an electrode. Okay, and likewise you can create an n number of regions. Okay, region 2, region 3, region 4. Likewise you can add it more regions. So based on your structure, you can add whatever you want. You can add it. Okay. So this is an electrode statement I have given, which is electrode and electrode number equal to 1, electrode there. And the name of the electrode I am choosing it as gate. Okay. and the coordinates I'm giving x coordinates from start with 0 and 0.4 to 0.6, okay, and the y coordinates it will be 0 and 0.1, and you can see here, so if we make it now, so it will replace this SiO2, okay, so but we don't want to replace this SiO2, so we have to make it upper, little bit upper. So what we'll do is we'll create one negative, we can increase its base, okay, increase the work area, okay. So how you increase the work area is, the rotation, you just make it one more, okay, you can give negative, so negative 0.1 you can give. So, and you can replace it here, okay. So minus 0.1 the y, and for x it will be 0. Okay. So now we just turn it. So you can see here, the gate has been formed as a conductor, but you can see in the other layers it was filled with silicon. Okay, so this happens because of this statement. We have not given any coordinates. Okay, and it will just fill whatever free area is there. It just fill. So now what I'll do is, I'll replace this with air. So I'll create a different region for silicon. So 0.122 for a silicon, okay, and rest other area I'm just filling it with air, okay. Yes, it will work. It will work. And there is a different type of writing the coding is there. So we'll see the second type also. Okay, for stacking different top and bottom method. So you can see here. First I will fill it with air. Okay, and SiO2 and the silicon. Okay, so just Yes, sorry. No, not space. So we have changed it in y coordinates, right? So only y coordinates will change. So we just run it and we'll see the maybe. simulator, we just see that. Okay. So you can see here. So this air and conductor is in same color, so that's why it looks like this. Okay. So you can change it easily by going to preference. So go edit preference, okay. And here I think some materials. Here is material, and air color you just change it. So air color, let's make it white. Okay. So likewise you can create it. Okay. Yes. So you can go to edit, preference, and lots of other parameters also there. Color, font, you can change. So if you have any doubts, please ask. So here the material, the gate material is just a conductor. We haven't defined what material it is, right? So writing a coordinate is like So what is this x minimum and x maximum? How you can give is, let's, for example, I want to create one box here, okay, one region here, okay, as some HF photo I want to create, okay, HF photo, okay. So how you give x minimum is this point, okay, and which is x minimum. X maximum is this point, okay, x maximum. And in the y scale, y minimum is this point, minimum and y maximum. Okay. So if you give these points, it will easily identify that box and it will fill that region. So wherever you give that value, it will create on that region. So, So if you face any issues, if you have any doubts, please ask. Okay.
कुछ चल नहीं, मैंने नहीं करा।
So and another thing is like you can highlight the electrodes. Okay, how you do this? So right click, display, and so I'll tell you what are these options are. So you can choose this electrode. This plus and minus symbol will be there. So if you select that, the electrode will be highlighted. Okay. So whatever electrode you choose, it will be highlighted. So if you have any doubts, or I'll just continue with this. So this is one way of writing a code and to declaring as electrode syntax. Okay. Or other ways, you can create a region of the electrode and you can no, not like that. This is a region number is separate, electrode is separate. No, that also you can link. That also we can link. I will tell you that how to do that. Okay. So now the second way of writing an electrode is writing in a region statement itself. So shall we proceed? Okay. So the next way of writing this electrode is writing it in a region statement itself. So how to do that is just with the material of aluminum, okay, and X minimum and same thing I have given. So now this electrode I am going to link this region statement. Okay. So this is an electrode and just you have to give region number equal to 4. So if you write it like this, it will be linked, okay, and the aluminum will be created. So there are different metals are available like gold, okay, copper is available, a bunch of different metals are available. I will show you that. So here you can see it was creating not well, right? So why this is because of the meshing is not enough. We have to make it dense in this area. Okay. So to do this, 0.4, we have to make another, reduce the mesh. So I have added additional points. So you can see, so based on this how the grids will form, based on that also only the structure will be created. Okay. So here the triangles are not made well. So it was a little bit loose, so I am making it dense. Okay. So and I will show you this grids also, mesh grids. Okay, I have made it a little bit smaller so that it will. Yes. So same thing, the electrode statement now, I just created with the region statement. Okay. So the region number 4, material is aluminum and its coordinates, x coordinate and y coordinates. Yes. I added here I added extra meshing points. So while writing the code you can optimize this. So no need to write at the beginning itself. So just give a basic points at the initial, and while writing the code you can optimize that mesh. So by this way it will you will not face the convergence issue. So if you have any doubts, please ask. So moving to the next step is called doping profile. So moving to the next step is we have made some region creation and we have placed the electrodes. So now we'll do the doping profiles, and how to do the doping profiles I'll let you know. Yes, sir. And so why I'm not creating it is, so creating a source and drain electrode, I'm just showing you how to create. Okay, so in the next step I will explain you all the things. Okay. So now I am going for a doping profile, which is, so let's make an N-type or P-type doping profile, and by coordinates also I'll show you. So this is the command. So if you do doping, and you can choose what type it is, an N-type, P-type, okay, or you can try this boron, accept boron, arsenic, okay. So different materials are available. You can choose that, okay, and also you can give like acceptor, donor, okay, like this also you can write, and you can choose what type of doping profile it should be, okay. So I choose uniform doping, you can choose Gaussian profile, okay, step profile. So different profiles are there, you can choose, and its concentration level. Okay. So the peak concentration level is 1e⁻15. So if you haven't provided any coordinates, okay, so what will happen is the entire device, the doping profile will appear. Okay. So I'll just simulate for both and I'll give coordinates also. So let's say for this, okay. So for this entire region, with all the materials we have done this doping profile. So we just see that. Yes. Yes, that also you can do. I'll show you that. So the same thing. So how to see the doping profile is, you can go to right click display and select the fourth option, which is called contours, and give OK. Okay. So you can visualize that by selecting the net doping profile. So you can see that N-type is been done. So here, so this option will be there for you. So you can see that different doping acceptor concentration, composition. So directly also you can select it. So directly also you can select. So some tools you can directly take it and use it. So if you go to this preference option and then choose in the toolbars shortcut, you can choose different options and you can bring it on. Okay. So moving to the next step is, so I want to create in only one single region, not on the other regions. Okay. The simple and easiest way is giving it in a regions. Okay, just give a region. Region equal to silicon, right? In a device simulation. Okay. The first thing is you have to declare, you have to call the device simulation framework. So here I haven't given the first thing, it should be Go Atlas. Okay. And the second things are like you have to create its work area. Okay. So for it, which one is an X coordinates and which one is a Y coordinates, that you have to define it. Okay. Okay, this is so here I have defined it. So this is x dot m, which defines x mesh. And L defines location. Okay, so here they have written in a short form. You can write it like x dot mesh. Okay, and you can give location, and you can use spacing. Okay, so I'm not going to directly create this. Okay, first I'll give you some. I'll just write it in the tech build window, and I will give you some detail. So I'm opening a new tech build. Okay. So first thing is I just going to create one basic structure, so that can be any device. So once you understand this coding, we can directly go for the NMOS structure creation. Okay. So first we have to write go atlas. Okay, because we have to call the device relation. Okay. So once you write go atlas, it will be highlighted in this white color. Okay. And the second line is we have to write mesh. Okay. So we have to introduce meshing. Okay. What is meshing is? Meshing is basically like in a structure. At the initial case, we are defining the work area. Okay. So let's consider that for x coordinates we are having a 1 microns, and y coordinates it was a 1 microns. Okay. So I'm writing mesh, and the second, so we start writing its coordinates. So the line, so this basic and all you can give it, it won't affect it. So here you can give a lot of space, no issues. So it's up to you. So each line it will take into a consideration for the simulation. You can write anywhere you want. Okay.
X dot.
No, in the same line you cannot write for all the code. So next line you have to write. So the starting location I'm giving 0. Okay. And the ending location of x I'm giving around 1 microns. Okay. And here you can see the location, and it's so the dimension, all the dimensions will be on microns. Okay. So if your device it's on like nanometer thickness, you have to convert that into microns and write it. Okay. So starts with 0. Okay. And you have to provide a spacing equal to. So I will tell you what is this spacing. Okay. So now the second point I'm going to write the x. I'm going to the ending point of the x, which will be 1 microns. Okay. So now I have created 2 points. So the one point of the x is 0, And another point, and we can see what is this spacing is. Spacing is how much sampling in between these points we can take. Okay. So for example,
जी मैंने देखा कि भाई ये एज एक्सटर्नल है मैंने पहले ध्यान
हाँ जी मैडम क्या सर
फोन साइज बढ़ा रेजोल्यूशन करो क्या
फोन साइज इसका
so let's consider this is our device. Okay. So this length will be 1 micrometer. Okay, which means 0 to 1. Okay, and for y, let's make it starts with 0 to 1. Okay, or 2 micrometer as per whatever wish. Okay. So first thing is what is the spacing is. Let's say it starts with 0 to 1. So how many grids we have to make? So for example, so if the total length is 1 micrometer, okay? So if you give the spacing is 0.5, okay, which is half of it, it will take 2 sampling, okay? It will cut into 2 and it will take 2 sampling, okay? So if you reduce it, like if you make it 0.1, so it will be total of 10, okay? So which means 10 sampling it will take. So why we will be doing this type of sampling is, this type of grid we create this. So basically like based on this only we will get the accuracy of our electrical characteristic extraction, okay? For example, okay. So for example, so not only X, in Y also we will do this griddings, okay? In Y also we will do this type of grids. So in each block it will be create one type of triangles will be created, okay? So in this each triangles our physics model will apply, okay? Like this drift diffusion and Poisson equations will apply and we will be extracting the electrical characteristics, okay? So for example, this is our transistor, okay? NPN transistor, okay? And the gate is there, okay? So if we reduce this thickness, like making a dense type of mesh, we will be creating it, the accuracy of our device will increase, okay? For example, so we are focusing on some parameters, let's say we focus on some threshold slope I want to analyze, and I want the exact results from an experimental paper, okay? So you have to give dense mesh, but if you give dense mesh, the simulation time will increase. It may take, sometimes it may take more than 1 hour more, and for a different complex structures, it will take more than 12 hours. Okay? So we cannot do the dense mesh every time. For example, we know this is our device, and we know this only in the channel area. This electron movement will be there, not in other areas. Right? So what we can do is only in those areas we can give dense mesh, okay? And in all other bulk areas, substrate area, we can give loose mesh. Okay. So this way we can say reduce the simulation time as well as we can increase its accuracy. Basically, we are optimizing it, and this is why we are doing spacing, and this is how we can do this. Yes, you can go negative value.
they